and good morning. My name is Gregg. I was just introduced. I work at Netflix. I've been giving both of these talks at various conferences to many practitioners who'd like to understand how to use this straight away. And what I like about ATC is many of us here are researchers and have the opportunity to work on and develop these topics further. Hands up if you'd identify yourself as a researcher. Okay, so this is most people, which is unusual for conferences I often go to. That's great because I think you'll find these two topics have many areas that can be developed further, and there's many opportunities for innovation. And so I would like to spend a lot of time on that, what the next steps and things we can do. The first topic is visualizing performance with flame graphs. Just to find out, has anyone used flame graphs already? Okay, so I've got like about 10 people. That's great. Flame graphs visualize stack traces, and the primary use for flame graphs is to visualize CPU profiles. I've got an example flame graph there. I haven't explained it yet, but it's showing all of the CPU cycles for a system, whether those CPU cycles are in the Java code that's running, whether it's in the kernel, or whether it's in user-level code. This is great for a performance engineer because I can look at a flame graph and identify where we should spend time optimizing. Netflix cares very much about CPU utilization. That's the key metric for which we scale our cloud. And if we can reduce CPU utilization by 1% or 5%, it's a very major win. And flame graphs have become a crucial tool for us. And also many other companies like Facebook use flame graphs as well, and Twitter and LinkedIn. And they've been sharing what they've done on their own blogs. So for this talk, I'll go through three parts. CPU flame graphs, which has been the primary case. I'd like to give you exposure into the challenges and issues we've had with flame graphs, which is fixing stacks and symbols, and then advanced flame graphs, what opportunities there are for future work in this space. Your takeaways will be how to interpret CPU flame graphs if you haven't seen them before, understanding pitfalls with their generation, and to discover opportunities. So I said I work at Netflix. We are deployed on Amazon for our streaming cloud. And we also have our own CDN, which is running FreeBSD. A lot of what I'm going to be talking about is used on our cloud, which is Linux. But we do also use flame graphs to analyze our FreeBSD CDN. To start with something to think about straight away, I still haven't explained what they are, but this is an example which has come up a number of times at Netflix, where the CPU time for an application is actually spent in exception handling. And since the way I've been creating flame graphs is to show all CPU cycles, whether it's in the application, whether it's in user mode, native libraries, or whether it's in the kernel, this is shown up quite clearly. People see these towers. They're in different colors. They shouldn't be there. This should just be Java code. And so they pop up, and they're very easy to identify. And the size of them is also relative to their proportion in the profile. So this has actually helped solve at least 2 performance wins at Netflix, just discovering that we were wasting time in exception handling. And it was very easy to identify flame graphs. So to go through what they do, with CPU profiling, there are a number of ways to do CPU profiling. A low overhead way is to do time sampling. And that's where I will have an interrupt that will wake up on all CPUs, maybe at 100 hertz or 1,000 hertz, and I'll grab the program counter or the stack backtrace. The advantages is it has low overhead. The disadvantages is it has coarse accuracy. So I may miss activity that happens between my 10 millisecond samples, but it's usually sufficient as I'm taking samples for maybe a minute or 2 minutes for an application. And I'll end up with thousands of samples, and I'll be able to see what's going on. As an example of on-CPU profiling, I've drawn a diagram which shows when the application is running on CPU, I can sample a stack trace. That might be function A, that might be function A, then A called B. when we block and we go off CPU, most operating system profilers will not continue to sample those threads. Some of them do, so there are wall clock time samplers or profilers, but most of the ones we're using don't. And so there's a different technique for attacking the off CPU time. At the moment, I want to think about CPU profiling. Stack traces, and I'm sure a lot of us know what stack traces are. A stack trace shows the code ancestry. So if I run JStack or if I use debuggers, it, in this case, is showing my Java main called function A, called function B, called function C. And you can imagine if you collect many of these at a timed interval and you can study them, you can understand why the application was on CPU. I said there's many system profilers, so Linux, the main one, the official profiler we use is perf events. There's also dtrace, can do profiling. OS X has instruments. Windows has xperf. And there's lots and lots and lots of other profilers. Flame graphs are not specific to a profiler. So a flame graph will visualize input from any of the profilers. I'll talk about Linux perf events. Now, it's a fairly advanced tool nowadays. It began life by instrumenting the performance monitoring counters, the low-level CPU counters that give us insight into cycles and stall cycles, cache hits and misses, things happening on the processor. Since then, perf events has had trace points added and dynamic tracing added, so it can do a lot more things. And it can sample stack traces of just about anything running on CPU. So any Linux server, if there are CPU cycles, Linux perf events can sample and tell us what it is. It can miss hard interrupt ISRs, which I've put a note for, but they're designed to be near zero and have separate tools for measuring them. I'm dwelling on this point because there are other types of profilers, like application-level profilers, that are blind to many areas. So at Netflix, we run a lot of Java, and there are a lot of Java profilers that use the JVM TI interface, and those operate from within the JVM, a user-level process. They cannot profile what the kernel is doing. Well, they could profile what the kernel is doing by using a kernel-level profiler, but they generally don't. So they stick to within their application boundary. And so that's why it's actually important that perf events has visibility of almost everything. It's a really good way of not having any blind spots when we do profiling. Has anyone used perf events? Linux perf events? Oh, so a lot of people, great. Here's an example run. I'm running perf record. -F99 means 99 hertz. -A for all CPUs, G for call graphs or stack back traces, and sleep for 30 seconds. There's a dummy command to give it an interval. When you run perf report, it will print a call tree summary that shows the code and the % of time in each of the code branches. So you can browse this. There's also an interactive perf report text user interface, and you can find out where your application is hot on CPU. Sometimes you can browse the output of perf record, and it works. In this example, and this is what we often have in real-world workloads, which are fairly complicated, the output of perf report is long. I had to truncate 13,000 lines for that screenshot. That's the full output of perf report, and that's basically unreadable. So as a performance engineer, this is disappointing. I need to be able to, especially at Netflix, in that we push major code changes several times every week. And so there is always a constant demand for rapid understanding of CPU profiles. I don't have time to spend 3 days reading this because the application will have changed by then at Netflix. I need to be able to understand the CPU profile in less than 5 minutes. I created flame graphs for this purpose. And a flame graph visualizes a collection of stack traces. And on the x-axis is the alphabet. On the y-axis is the stack depth. The color of flame graphs is random, or I can use it as a dimension. So if you can imagine taking those stack traces and then coloring them as towers of vertical rectangles, and then sorting them so that the same functions are adjacent on the x-axis, you can then merge those rectangles. And when I designed flame graphs, I found an effective way to maximize merging was to sort the x-axis based on the alphabet, to do an alphabetical sort of the stack trace. If the first level functions was function A, and then there was function B and function C, it would group them together, and then I could make the box wider. And that's why we end up with these long rectangles. What this is actually visualizing is hundreds, if not thousands, of stacked samples. Each of them would appear as a very thin tower, but I'm merging them together so that you can see where the bulk of the CPU time is. Some people find it confusing because there have been similar visualizations in the past that don't put the alphabet on the x-axis. They put time on the x-axis. That's not what flame graphs do. With flame graphs, if I put time on the x-axis and I'm sampling at 10 milliseconds, the applications we run may be running an entirely different code path every time I take a 10 millisecond sample. And I'd end up with something that couldn't be merged. It would just look like noise. So by being able to shuffle around those stacked samples, I'm able to merge those frames together. The flame graphs, I have an implementation of flame graphs that's open source on GitHub, which I wrote in Perl. I'm also helping with a newer D3 version. Many companies have done their own versions of flame graphs. The flame graph itself is not a complicated visualization. I think if you were interested in flame graphs, but you really didn't want to use my Perl program or my D3 program, you could probably write a flame graph visualizing tool in one day if you're good at a programming language. It's not that complicated. I wrote an article about flame graphs for Communications at the ACM, and as part of that, did the history and research into the visualization type, and it's an adjacency diagram that uses the hierarchical layout. So the actual visualization type has been known for decades, if not hundreds of years. I'm applying it to stack traces that I've sorted alphabetically. How to interpret a flame graph. If this was my flame graph, the y-axis is stack depth, going from bottom up. So A would be the great-grandparent function, A called B and H, B called C, C called D, and so on. Did A call B for a while and then call H? We don't know. I do not have timestamps in the flame graph. The reason why B is on the left of H is because I've alphabetically sorted those samples. It's not because B ran and then H ran. So this is the number one confusing thing people find about flame graphs, because so many visualizations are a time series, and we have time on the x-axis, and that's not what I have here. It's more like a pie chart class of visualization. I'm showing it's a representation of all of the data. The top edge of the flame graph, for a CPU flame graph, shows what is running on CPU directly. So if I looked at that flame graph and I wanted to know who's consuming the most CPU cycles, it's G, because it's the biggest. The wider it is, the more samples there were for that. This is great, because humans are really good at comparing line lengths, and not so good at that giant wall of text I had earlier, where you had to read the numbers to figure out where the code paths were. So I could just look at a flame graph, look for the biggest top plateau, and say, that's an interesting area to optimize. If we can eliminate that, we'll get the biggest performance win. So I should be looking at function G. But going back down the stack is also interesting. I might look at function G, and function G is really boring. It might be spin lock. It's like, well, I can't delete spin locks. They must be used for something interesting. And so I work my way down the stack until I find some high-level function that can be optimized. So G is called by F, which is called by D, which is called by C, and so on. And as I mentioned, widths are proportional to presence in samples. So comparing B to H, I can just look at it, and B looks like it was part of the profile 4 or 5 times more than H. So widths are great. Now, one thing that the slides can't do is show you that these are actually interactive. So let me just switch to a browser. So this is a flame graph I collected earlier. I'm going to zoom in because it's actually scroll over the screen. Okay. Now, if I mouse over functions, at the bottom of the screen, I print some information. It also does it as a tooltip. So there's IPQ transmit, 10.5% of samples contain that. And I can work my way up and discover all sorts of interesting things. So this is visualizing the code flow. So sys write called VFS write, called underbar VFS write, and so on, all the way to what was on CPU. In fact, there's a plateau. If I click on it, I can zoom in by clicking on areas of the flame graph. That's Zen Hypercal Zen version. I collected this flame graph within Amazon EC2. It's running as a Zen guest, a hypervisor, and Zen happens to use the version call to see if there's any pending events. So you actually see it quite a lot. It's there because I'm in a hypervisor, and it's actually doing I/O because we're in TCP. TCP v4 receive, sock, def, readable, and so on. Over here, I have some Java frames, and I can see at this point, my Java, I have a lot of close frames, and they've called into socket close, and socket close has ended up calling into TCP push pending frames, and so on and so on. Great for understanding software. If I'm looking for performance optimizations in this, I'm going to look for the biggest areas. So you do have a chunk of time in the kernel, and I can quickly mouse over it and see where it's coming from. But maybe a frame like this would be the biggest time. And this is not actually a very interesting application I'm running. I'm micro-benchmarking VertX. But I'd start with something wide, maybe down here. Or if there was a very large plateau, that would be another good target to start with. Flame graphs are also really good for just understanding software, period. The kernel has millions of lines of code. Netflix applications, we have many, many lines of code internally to run Netflix. And if you're new to a code base, it can be intimidating because you're looking at many millions of lines of code. If you start with a flame graph, you've narrowed down the operating table to just the functions and methods that are being called. And also shows you the relationship of how they're being called. And it shows you the importance of how they're being called. I can see the hot path, because it's usually the widest. That's what's on CPU. So flame graphs are also very useful simply to explore the unknown software and get your head around it, around its internals. One other demonstration I can do while I have this open is if I do Control F, I can do search terms. So I just typed in TCP, and it will highlight every frame with TCP. And on the bottom right, it will print a matched percent. So 24% of the frames contain TCP. And that's excluding vertical overlap. This is really important as a performance engineer because I often need to know how much time is spent in this module or this function, even if it's scattered all around the place, so that I can then do estimated speed up. So I can search for anything. There's a lot of JavaScript in here too. 32.9% is in JavaScript, at least the Java that's running JavaScript, because this is the VertX. So zoom, search, and mouse over, that's about it. So this is a very basic flame graph implementation in Perl that only has a few of these interactive features, but they've been tremendously useful. I wanted to highlight that because I think you can add a lot more interactive features than those 3 alone. And so that might be interesting to see what else can we do if we want to add interactivity to these. Mixed mode flame graphs are where I'm showing user-level code with kernel code together. It's a little bit of a hack, but in my implementation, I've colored different types of code. So for jittered code, I color it green. If it includes inlined calls, I'll color it aqua. Red for user-level code, orange for kernel, and yellow for C++. The intensity is randomized for mixed mode flame graphs to differentiate frames. If all the frames are of the same color and there's two stacks close together, it can be hard to see that there's two towers close together. And so the initial flame graph, I really randomized the warm palette, and it really helped things stand out. People also said it looked pretty, and so they liked putting flame graphs in their slide decks, but it had a function as well. Another way to use the intensity or saturation is to hash it on the function name. So the same function has the same color saturation. That example I've got in the slideshow, I'm using hashing on the function name. Does it look like you can tell that the saturation's varied a lot? No, I don't think I've got that algorithm right. That's another area I think we can improve is hash. How well can we hash based on a function name? Just so that visually you can see the same functions are in different areas, different towers. So that's something that we can improve. Another flame graph type we can definitely improve for future work is differential flame graphs. At Netflix, like I said, we're pushing code often, and it's not so much where's the bottlenecks in the new code. We also want to know how did the changes to the new version of the code differ to the old version of the code. And what engineers, including myself for a long time, have done is loaded the flame graph for the old version and the flame graph for the new version in separate browser tabs, and then flicked between them like searching for Pluto. And you go flick, 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 and go, oh, this tower is appearing in the new version, it's disappearing in the old version. And that served us okay for a while, but something that we should explore is, can we have a single flame graph that shows the difference between two profiles? I implemented red-blue differentials, and they kind of work okay. And so what I do is I draw a flame graph based on profile B, and then I look at the difference between profile A and profile B, and if functions have more samples in profile B, I color them red, and if they have less samples, I color them blue, proportionally. So you look for red, which means code increased, and blue, which means code decreased. Great, sounds like problem solved. Not so fast. What we often find is, with code changes, in profile B, towers can be eliminated. So I have nothing to paint blue, because it's gone. And that's actually a little bit misleading. I've got another example of a differential flame graph later that a researcher came up with and wrote a paper on called Flame Graph Diff. And that's where he uses 3 flame graphs. He shows I'll get to it later. Just to solve that one particular problem of we don't want missing towers, we don't want to mislead the end user. But I think it's another interesting area. What we want with Netflix, and we've been playing with it, is when we deploy software, every time we deploy software, we should be able to have a flame graph diff automatically generated for that new software version. So as part of our Jenkins build process. We also have automated canary testing. So we have lots of places to put this in. What we want is a really good visualization that's going to work. And my red-blue version does have the caveat that if something eliminates entirely, it won't be there. Maybe there's ways to fix that. Icicle graphs. Flame graphs merge bottom up. So if I'm a thread, it's going to merge from start, main, and then the great-grandparent function and its children and so on. Sometimes it can be helpful to merge top-down instead. And so this is a great example where the flame graph looked like noise, just all these thin towers. And I flipped the merge order to merge top-down, and I could see that from all different parts of software, it was calling the same kernel function. And it was actually an interrupt, and it was calling NUMA rebalance. And so this was an issue on a particular Linux kernel version where this was actually taken off production at Netflix, where we were spending 60% of CPU time doing kernel NUMA rebalance. NUMA rebalance is supposed to be a performance optimization where you move pages around on a non-uniform memory access system to make things a little bit faster, but to spend 60% of your CPU resources pinging pages around from one node to another doesn't make any sense. But the way it manifests in the Flame Graph is the kernel would keep interrupting applications and do a little bit of work. And so you had like rain, the same kernel stack fell like rain on all sorts of different application areas. And that's why we got the Flame Graph on the left. Something I want to do in the D3 version of Flame Graphs, I said we'd only done 3 things for interactivity, but if there's a 4th, I would like a button that says flip from bottom merge to top merge. And so the Flame Graph would flip around. Currently, I have to regenerate it. There are options in the Flame Graph Perl program to do this. Flame Graph search, I already mentioned, very useful. So you can search, and it also adds up the cumulative time. Sometimes you need to understand a function that's scattered all over the place. And it's just quick. Flame Graph search will tell you the cumulative time. Flame charts I want to mention, because they're not flame graphs. So a while ago, someone filed a ticket for Google's Chrome developer tools, what it was called before then, to implement flame graphs, which would be great. Instead of implementing flame graphs, they put time on the x-axis. Fortunately, they called it something different, so they call it flame charts. And so now we kind of have this terminology where it looks like an upside-down flame graph. That's fine. It looks like a flame graph, but it's not. It's times on the x-axis. That is a flame chart. It's useful for solving different types of problems. So perhaps how things change over time is interesting. It doesn't really work for the applications I'm analyzing because they usually have many dozens of threads running at the same time. Why it works so well for Chrome DevTools is they are profiling V8 JavaScript, which is single-threaded. And so you can have a thread go into a function for 100 milliseconds, and you have one long rectangle wide enough to draw the function name. If you're on a multi-threaded application and you have all samples coming in at the same time, then it's going to be noise. It'll be a mess. You can't merge things together. Or you could do a separate flame chart for each thread is one way to solve that. But yeah, applying flame charts to multi-threaded applications is not, maybe there's a better way, but at the moment, the best way I know is to do a flame chart for each thread. I want to summarize some of the issues quickly that you'll encounter with flame graphs. Stack tracing. Broken stack traces are common with profilers. In Linux, I run perf script, and it tells me that Java has 1 frame of the stack, or 2 frames, which is bogus. The stack's going to be pretty deep, and it's probably going to end in start thread or main. This happens because compilers like to reuse the frame pointer register as a compiler optimization. That's RBP on x86, x86-64. And the default way that profilers capture stack traces is to go to the frame pointer register. So a stack trace is a linked list, and if you're a debugger and you're interrupting an application mid-flight, it's really handy that the application, by convention, leaves the frame pointer register pointing to that linked list, so that you, the debugger, can say, I will read RBP, now I can go and find where the stack trace is. However, a long time ago, compiler engineers thought, there's not enough registers on x86, which there wasn't at the time. How about we take RBP and we use it as a general purpose register to get maybe a 1% speed up in spec CPU? Okay, fine. And I'm sure it did make a bigger performance difference at the time. However, it broke profilers, because now we can't walk the stack trace because you're using the frame pointer register for something that's not the frame pointer. So that's really annoying. If I were to draw that as a flame graph, my Java functions look like this grass at the bottom because the profiler can't walk the flame graph. Not a bug with the flame graph visualization software. This is a very common bug, common situation you'll encounter with profilers. Lots of different ways to fix it. So you could use frame pointers again. So GCC has -f no emit frame pointer. The Linux kernel, by the way, is by default, most distributions compile with the frame pointer. So you can always profile the kernel. I wish applications would do this as well. We have more registers. It's not that much of a performance hit, usually. So frame pointer-based stack walking is nice and simple. There is debug info-based walking, where a lot of information is stored with the application so that a debugger can then figure out where the stack is without the frame pointer register. Linux has dwarf for that. It does work, but not all profilers speak dwarf. It also costs disk space, since you need to install the dwarf symbols as well. They can be quite large. They can get, debug info for the kernel can get as big as 1 gigabyte. Another way to do it is to have, if you're a runtime, you can have your own walker. So Java has its own walkers. In fact, they need to because a lot of these runtimes have exception handlers. So when the runtime crashes and it says, hey, I crashed, here's the stack trace of when I crashed, it has to be able to generate that stack trace. It has to be able to walk its own brain and figure out where it was. So these runtimes often come with stack walkers, which is great. They have an advantage in that they can get more information out because they're designed for Java or Python or Ruby or whatever it is. A disadvantage is they're limited to application internals. So Java's JVM-TI stack walker can't walk into the kernel and tell you what's going on there. And there's another one which has support in Linux down. That's last branch record. That's an Intel low-level CPU feature which will record a ring buffer every time an instruction does a branch. And you can narrow it down to just the call type of branch. And then you can read that buffer and then synthesize the stack trace. It's fairly wild, but I know Intel engineers get really excited about it because it does work. And you don't need either dwarf and you don't need frame pointers. You're just relying on hardware to go and remember every time it did a call-based branch. And then your profiler reads that buffer later. Anyone used LBR to profile? There we go, someone's used it. Do you like it? All right. It does have some caveats, like it depends on the CPU, maybe it's limited to a certain depth and things like that. So I have not used it yet because I am doing most of my analysis on the cloud, and LBR is one of the advanced features that often gets blocked by hypervisors. So I can't access LBR. That's okay, I use the other ones. Java is a special case with stack traces in that this is not GCC, but it's rather hotspot. C2 compiler would reuse the frame pointer register. And I prototyped a JVM fix for that. And Oracle were nice enough to take it and then rewrite it and make it nicer. And it's now in JDK 8 update 60 build 19. So you can do -XX plus preserve frame pointer and you get Java stack traces. Just as an example of fixing a runtime to do this. And if you fix your Java stack traces and do a flame graph, great. You now don't have this grass, you now have a tower, but jittered runtimes in particular, you may be missing symbols. So it just has unknown everywhere. I'll show how to fix that in a moment. A couple of other challenges. One is inlining. Inlining is another compiler optimization. Compiler optimizations are the bane of performance engineers, even though they're supposed to help us, right? But they make profiling difficult and debugging difficult. Java, in particular, can inline. In production, I see Java inlining about 66% of frames. So the tower is only a third as tall as it should be. 2 frames out of every 3 have been inlined. Java, by default, you can tune it, can inline up to 9 levels deep. Can you imagine losing 9 frames and then trying to understand the stack? Fortunately, when you're only losing 2 out of every 3 and you browse the stack and you understand you're missing these frames, you generally can make sense of it. And why you're missing it is when you're using a system profiler like perf, it's walking the frame pointer register. It's not asking Java, hey, did you inline something? Can you resuscitate the inline frames? There are ways to resuscitate the inline frames, and Java's perf map agent can do that with the unfold all option. And you can also tune inlining. So you might want to relax inlining a bit because if it's going too crazy. Stack depth has been another challenge of profiling, and we found that Groovy in Java would build these very deep stacks that broke Linux's 127 frame limit for perf. And Arnaldo fixed that in Linux 4.8, which is great. So we can now tune the stack depth to whatever we want, 1024. The flame graphs are really crazily tall, and that's kind of a sign that maybe something else is wrong, but at least we get to see the full flame graph. The problem is if you have truncated stacks, the flame graph doesn't know how to assemble it together. And so on the left is a picture of a broken flame graph where you just have all these detached thin towers, which are supposed to be part of the main tower. So those are a few challenges with the stack walking. With symbols, fixing native symbols. So my binaries that I have on Linux, you can often fix them by installing a debug symbol package. Unfortunately, they often get shipped stripped to save some bytes on disk. And so they often don't have symbols by default. Usually easily fixable, or you can recompile from source. Jittered runtimes like Java and Node.js are more complicated. And this is another area where there may be some more work. So Linux perf, when it's profiling a jittered runtime like Java, it will look for an external map file. Like Linux perf has been designed to fix this a long time ago. So it will look for a /temp/perf-pid.map with the process ID as a supplemental symbol file for your runtime. So if you invent a new runtime, like myfancylanguage.io, please add an option to write one of these map files so that perf still works. It's a very simple text file. That can be created by runtimes like Java's perf map agent. So, running Java with -XX preserve frame pointer and using the perf map agent, I get my full mixed mode flame graph. Full stack traces, symbols. I'm talking about Java a lot because Java's actually, we do use it a lot at Netflix, but it's also a very complicated example of profiling because it does ditch the frame pointer by default, and it does jittered just-in-time compilation, which doesn't have a traditional compiled symbol table. So if you can get Java to work, you should be able to get anything to work. And zooming in, I did that earlier, so we can see the Java frames. There are still some problems for us to work on with this idea of having an external symbol file for JIT. If you look at Java, and you can turn on debug options so that the C2 compiler will tell you what it's doing, Java's compiling all the time. So it's frequently trying to do different compilations and test things out. Now, think about it. I do a performance profile for 60 seconds. Now I run perf map agent, which takes a snapshot of the symbol table. And now perf uses that to translate my 60 seconds of profiling. The problem is, during that profile, some methods may have moved because the C2 compiler moved them around. And so my snapshot will mistranslate some symbols, symbol churn. How can we fix that? Well, one thing I'm looking at is to take before and after snapshots for the profile. And then I diff the snapshots. This is just a symbol table. And if things have moved, I flag them in the flame graph as suspicious. So if this address used to point to function A, but now points to function Z, I should color it yellow in the flame graph and say, I don't really know what this was because it changed. JIT changed what was in instruction memory. There's another way to do it that Google worked on, Stefan Iranian, and that is to do time-stamped logs from Java's compiler. I find this a little heavyweight. I like to constantly log what Java's compiling, but it's impressive that perf, all the mechanics are now there for perf to use it. And there are some instances where I do want to use this. So way, perf can read in a different type of supplemental symbol file that has timestamps. So it knows the state of memory for every sample in the profile and can translate correctly. Containers is another big problem with symbols in Linux because perf is not container aware yet. And so perf will look for the temp map files in the host. If you're running perf from the host, it'll look for them in the host, but they're actually in the container. It will look for binary symbol files in the host when they're actually in the container. I'm helping Kirsta Johansson. He's proposed a fix on LKML right now to fix this. So hopefully they'll get into Linux 4.13. So those are some of the technical challenges for flame graphs. Now, to summarize instructions, these slides will be online, by the way. I put all my slides on SlideShare, and USENIX may put them on the website too. So instructions, on Linux 2.6 onwards, you can create CPU flame graphs by using my Perl program, or you can write your own, doesn't matter. Then perf record, so there I'm saying 99 hertz on all CPUs for 30 seconds. Perf script does this dump of every sample, and then I feed it into stack collapse, which turns these multi-line stack traces into single lines, into a standard format for flame graph to ingest. Then flame graph will spit out a perf.sfig. Why I split it up into 2 steps, why don't I just pipe perf script straight into flame graph, is because there are different stack collapses for the different profilers. So there's a stack collapse for instruments, and for dtrace, and for ETW for Microsoft. And like, it's very easy to write your own. Just write it in awk, or Perl, or shell, it doesn't matter. And so you just have to take the output of your profiler and then emit it in this colon delimited single line format for the profile. People have written converters for lots of things. That's how it used to be for a long time. Linux 4.5 added a way that perf can do some of the summarization first. So we sort of eliminate the stack collapse step. Linux 4.9 added BPF access to time sampling, which is a big feature. And that means we can do the aggregation in kernel, and you can have the kernel emit the format that flame graph ingests directly. So we skip these user-level post-processing stages and file system writes, which is really cool. Looks like this. So Linux 2.6, we perf record, we write to a perf.data file, all those samples. That perf.data file may be tens or hundreds of megs. We post-process it using perf script and stack collapse. That takes seconds and seconds and seconds of CPU time. Not to mention the file system writes, because I had to write out perf.data. Go to Linux 4.9. I worked on this stuff. This is much, much better. So now with BPF, which I'll talk about in the next topic, with BPF I can tell the kernel profile and aggregate those stack traces, and then just dump me the output. Much more efficient. If you want instructions for a particular language or runtime, do an internet search, because there are often caveats and quirks for different things, and people have generally figured them out. I'm trying to document them all on my CPU Flame Graphs page. Another thing I should include in instructions is people at Netflix don't log into instances and run those shell commands that I included. Sometimes we do. A lot of people will use an open source instance analysis tool I'm working on called Vector. And with Vector, there is a CPU Flame Graph button, and it will just go and generate flame graphs on demand. And so engineers can just click a button, and then 30 seconds later or 60 seconds later, they're looking at a flame graph. And flame graphs are starting to appear in other commercial profilers and performance analysis tools. And they should be part of everything. CPU profiling is a very common task. Last topic is advanced flame graphs. And this is where there's a lot of opportunities for interesting work. Flame graphs just visualize a collection of stack traces. This is my diagram of the kernel and showing how Linux has event sources for instrumenting all sorts of different areas. All of these areas I can pull out stack traces from. I could pull out stack traces for page faults. I could pull out stack traces for block I/O. I could pull out stack traces for PMCs. I could say every 10,000 cache misses, give me a stack trace. So I can take those collections of stack traces and I could do a disk I/O flame graph, or a network flame graph, or a CPU stall cycle flame graph. The thing you've got to check is if it is happening in the context of the application. There are some areas of the kernel which don't. So if I do a bunch of file system writes, so Java's writing to the file system, the kernel will cache that, and then it will write that cache back later, flush it to disk. So if I try and capture the block I/O on disk writes, and if I'm hoping to see my Java stack backtrace, I'm probably not going to see it, unless it's doing synchronous writes. I'm probably going to see some kernel task that was doing catch-up and flushing them out. So when you're browsing this and you're thinking, oh, wow, this is awesome, I can do flame graphs for all these things, think about the synchronous context. If you want to go all the way back into your application, then the event has to happen in that application synchronous context. Or you need to stitch it together later somehow. Page faults are a great one. They happen in application context, and perf supports it. Page faults are when because most operating systems are on-demand allocation. So you malloc a gigabyte, the kernel lies to you and says, sure, you've got a gigabyte. Then you start accessing the pages and the lie is revealed. When you access the pages, the CPU gets a hardware fault because there was no virtual to physical mapping. Then the kernel has to make good on its promise and then coordinate there to be a page attached. I like this type of flame graph because page faults show when your RSS, your resident set size, is growing. And it's also low frequency, so it's a very low overhead way of getting one look at memory leaks. And so you can do flame graphs for page faults. I've got a diagram here showing memory allocation. And you can think of all of these as sources for flame graphs. So I can do malloc free. I could do it when we grow our heap via the break syscall or map and unmap. I can do it on page faults. Each of these has different levels of overhead. The malloc and free levels of flame graph, malloc can happen very frequently. And even though the profilers have low overhead, that can still start to be prohibitive. That's another area of work that they're working on, is lowering the overhead of user-level instrumentation to make things like malloc tracing more feasible. Context switches is another great source. You can say why Java blocked and stopped running on CPU. Every time a thread stops running on CPU, the kernel runs its context switch routine. What a great area to instrument, because then I can pull out stack traces of why I blocked and get insight into what's happening off CPU, not just on CPU. And I've used that plenty of times for discoveries. Like I was analyzing the difference between frameworks. Disk I/O. If you instrument block RQ insert, that often does happen in synchronous context, so that's when things are added to the queue. It will then happen later. So you often can do flame graphs based on that probe for disk I/O. TCP events, another great target. Why are my applications doing so much networking? I don't understand. Or maybe there's paths I've forgotten about because my application is this giant monolith. I can create a flame graph and identify all the reasons why I'm doing TCP transmits or TCP connects or accepts. Cache misses. So I might want to go down to the hardware and say, show me last level cache loads and misses, stall cycles. I can do a flame graph for that. That's great as it gives me insight into not just that you were on CPU, but what was the CPU doing? Was it making forward progress with instructions or was it blocked? There's one version of this flame graph that our CDN team is using on FreeBSD called a CPI Flame Graph. And that's where I'm using my differential code, but I'm using it to show the cycles per instruction for each frame. So now you look at the flame graph, and the wider it is, the more it was present in the sample. But the color tells you what that frame was doing. If it's red, it means it was executing many, many instructions. Maybe it's a spin lock or something. If it was blue, it means it was not executing lots of instructions. It was cycle heavy, probably stall cycle heavy, probably memory stall cycle heavy. So now the developer can look at the flame graph and not just see the big parts, but have an insight as to why it was big. So it may be big because they're just doing lots of memory I/O, and that's dominating. Off-CPU analysis. That's another type of flame graph we can do. And I've drawn this very generic thread state transition diagram. And you can imagine attacking all the thread states that aren't on CPU. And so if I'm doing a waiting on resources, acquiring locks, and so on. So an off-CPU time flame graph can instrument every time you block, measure the time you blocked to when you came back on, and then display it. So here's an off-CPU time flame graph showing kernel stacks. The wider it is, the longer you were off CPU. Zooming in. So I've got, on the left, I can see, at the bottom it says it's the tar command. On the left I can see maybe 5% of my time, tar was blocked doing directory reads because I can browse that stack trace. In the middle, tar's doing file reads from disks. So I can see VFS read, generic file read, iter, and then it's going into disk I/O. And on the right, there's these thin paths of doing other types of reads. This is great for understanding the flip side of CPU time. This is off CPU time. Why am I blocked? And what are all the different reasons I've blocked? And again, it's all proportional. So you look for the widest stack trace that tells you where it's spending most of its time. TAR's spending most of its time reading files from disk. Not a big surprise. Great. Now that we can do CPU flame graphs and off CPU flame graphs, you'd think that maybe we can solve every performance issue possible. Maybe I can retire. That's it. I'm done. I'll just add an off CPU button in our vector instance service at Netflix, and that's it. Unfortunately, when you start looking at off CPU flame graphs, and I've got the instructions on my blog post for generating these, you often see things like this. So here's gzip. Gzip is calling syscall fastpath, sysread, VFS read, pipe wait, and then we're blocked. So what's gzip blocked on? We don't actually know. It's blocked reading a pipe. It's actually blocked on someone else. And this often happens in software. So if you generate off-CPU flame graphs and think, this is the best, you'll probably find that 60% of the stack traces you're looking at, they're blocked on someone else. And so you have a very boring stack trace. It could be, I'm blocked on a spin lock or a mutex, adaptive mutex. It's like, okay, but why were you blocked? Like, what took so long to wake up? So you need more information. Off-wake flame graphs. These have only been possible recently with Linux BPF because we can instrument not just when you block and when you wake up, we can instrument when the kernel does wake-ups, because that's just software, and then BPF lets us stitch together those stack traces in kernel. Zooming in on this, so at the bottom, there's gzip. Gzip was blocked on pipe wait. And then I've drawn the waker stack. I've actually flipped its order because I think it makes more sense. So you can read that top down. Gzip was blocked on tar. Tar was doing syswrite, VFS write, and then pipe write. The reason gzip was blocked on tar was I was doing a tar pipe gzip, right? And so a very common Unix command. This is great. I think I've got an example of one of these. Okay, so here's an off-wake time flame graph, and I can browse around. Here's SSHD. It's blocked on select. Again, pretty boring. I don't know what that means. But if I come up here, I can see, oh, it's waiting for TTY input. So this is the SSH session waiting for some human to bash on the keyboard. And so you can browse around. There's my gzip tar stack and learn a lot of things. There's tail. There's the tar with the different stack traces, and there's tar getting blocked on doing directory reads and so on. Okay, so now I've solved every performance problem with off-wake time flame graph. Now I can retire. Turns out no, because one wake-up stack is often not enough. And talking to some other performance engineers in the industry, they say sometimes we have to unwind 7 stacks to get to the root cause of the issue. And so some thread got blocked, and that's the actual issue. It woke up another thread, which woke up another thread, which woke up another thread, which ultimately woke up our blocked application. And you need to see the entire chain. So in development, I am working on chain graphs, and that's where I stitch together the entire chain. I have published some stuff on this. I don't have it finished. So this is in development because it's quite tricky. So now we're handling a lot of instrumentation in the kernel, and there's lots of challenges with that. So that's an in development area. But if I succeed, then maybe I can retire. Now, there will always be something else. Tooling will just get better. Another area I have not solved is if we have this great ability to do CPI Flame graphs and off CPI Flame graphs, which is still useful, can you show them both in the same timeline? And well, you can, but often the CPU flames will get shrunk down. Because if I have a multi-threaded application, so I've got Java and it's got 50 threads, it may only have 2 of them on CPU at any given time, and the other 48 are waiting for work. And so the resulting flame graph will be dominated by those 48 threads just waiting. How can we fix this? I don't know how to fix it. So this is an area that has not been solved yet. One thing I find irritating is, if I go back to my diagram, this is a generic fantasy thread state diagram. I have a thread state at the bottom called idle waiting for work. There's no such thing in Linux. So the Linux kernel does not know if an application is waiting for work or if it's mid-flight of a request. If it did, if it knew that this application is just waiting for the next job, it's totally idle, I could then eliminate it out of the stack trace, out of those off CPU flame graphs, so that you just focused on the wait time during a request that you cared about. But we don't have that thread state. I don't think that thread state exists in any operating system kernel. So should we add that thread state? How would that work? Would your application need to make syscalls every time it went to sleep, waiting for the next request to say, hey, kernel, I genuinely am asleep. Like, I don't care. I'm just waiting for the next thing. And so then the kernel had the state so that it knew to separate out the totally idle frames from in the middle of request. I bring that up because that's unsolved. And another thing which is really important that we're still working on, and I'd love to see other people try it, is coming up with flame graph differentials and improving that process. So this is one that Corporal Benzema came up with, and he did a paper on it, flame graph diff. And so he shows on the top left flame graph, it is the difference if you switched from software version B to A. On the top right flame graph is if you went from software version A to B. And then the bottom flame graph is just the difference. So you can, if you're considering whether to deploy a change, you can look at all 3 flame graphs and decide, is this good or bad? Pretty good. It's complete. It doesn't suffer the problems my version did. So that's some really advanced things. And so the takeaways from that is how to interpret CPI flame graphs, understanding pitfalls and stack traces, and all these exciting opportunities for future development. Again, these slides will be published. I'll take a couple of questions, and then I'll do the next topic, and then I'll take questions until the end of the time. Yes? Thanks.
So for your comment about wanting to know when you're asleep waiting for another request, it would seem to me that a really good thing to be able to do is to have, for example, if this is an RPC type server, a way for the user space RPC layer to say, I'm starting request serial number XYZ. And that means, number one, you know that you're now in the middle of servicing a request, and number two, if your RPC layer is doing some kind of cross-cell or cross-cluster logging, you can tie together the tracing from the upper layers to the kernel tracing.
Yes, so some applications already have baked-in instrumentation to say when they're starting and ending requests. And if you use dynamic tracing tools, you can leverage that. but it differs per application. If it was a standard, right, that's what we want. So this is what I can rely on. All applications are going to make these. I'm beginning work, I'm ending work. That would be great. So I'd love it to be a standard. It would make my life easier. Yes?
Just to add on this point, I think, I've debugged a lot of problems, but I feel like the stack traces for if you're waiting for something, as well as if you're doing some work and waiting to do something, so the stack traces should be different. So you should be able to differentiate, like if these are actually waiting for new requests to come in and filter those out. But
yes, so the stack traces should be different if you're waiting for work and not. Sure. And one solution might be to come up with a Rolodex of here's the functions that generally mean I'm waiting for work. And so maybe there's a bunch of C functions that you expect applications to call in between requests or during a request. So you could come up with some regular expressions. It's kind of a hack. Like I'd rather there to be an API for applications to inform the kernel. But yeah, sure, as a human, you can look at them and say, oh, that's waiting for work and that's in a request. So currently, currently we make sense of it, right? Because we're humans. I would love there to be an automatic way to just take out the non-interesting off CPU stacks without human intervention.
Are there problems that you find which are like, you still think the flame graphs are not good fit for it?
The wake-ups are still pretty good, but we have to keep walking chains of wake-ups. And so that's where things get problematic. OK, I'll do the next topic, but feel free to ask me more flame graph questions at the end of this.